Okay, YouTube, this is my second video on multiplying and dividing rational expressions. And in our first video, we looked at just writing expressions in simplest form. What we're going to be doing in this video is just take it that extra step and go ahead and multiply a couple rational expressions and then simplify them as we did in the last video. So I can say here that the rule for multiplying rational expressions is the same as the rule for multiplying what we call numerical fractions. And so that is to say that when you look at two fractions such as this, a over b times c over d, essentially numerically we would just go ahead and multiply this straight across. And so what we end up with is this AC over BD, and simplifying it if possible, but given that B and D both don't equal 0, then this is going to be our product right here. And so we're going to treat this very much the same way when we deal with algebraic expressions, such as say 5x squared over 2xy squared times 6xy cubed over 10y. We could go ahead and multiply these straight across. And so what you'll see is pretty simple here. We're using our rules of exponents. For instance, here we get 5 times 6 is 30. X squared times x to the first is x to the third, and no y's times y to the third is y to the third, whereas on the bottom we get 2 times 10 is 20. X to the first times no x's is x to the first, and y squared times y to the first is y to the third. So what we end up with is this expression here that, if you've noticed, can be simplified. That is to say, we could factor the top and the bottom. So the top and the bottom, they do, and in this screenshot here, a grand job of factoring this out, but they factor out into common factors. So for instance here, 30 and 20 share a common factor of 10. So 30 is 10 times 3, 20 is 10 times 2, and we could ditch the common factor of 10. Likewise, we could say that x cubed and x, they both have an x in common. So x cubed is really x times x squared over x. We don't always have to rip these apart like has been given here in this screenshot, but we can see that an x cancels out on top and bottom, leaving behind two x's on top, and then our y's cubed on top and bottom, those just straight up cancel out together. So what we get left with is this 3x squared on top and this 2 on bottom. So now, one thing I do want to notice is that they, in this screenshot, have written a restriction here that x and y are not allowed to be 0. And the reason why is because, again, we cannot have a value of 0 in the denominator. So if we were to set these factored expressions equal to 0 and solve them, well, then either x equals 0 or y squared equals 0. And in either case, we get x and y come out to be 0. And the same thing here, y cannot be equal to 0. So we want to make sure that we restrict our domain, but also that we restrict our domain based upon our simplified expression, which in this case has no variables in the denominator, so we don't need to worry about that as much. So to break this down, I suppose I would put this into a series of steps here. Number one being this factor all numerators and denominators. So factor all numerators and denominators. Okay. I'm going to go ahead and say we're going to multiply up front, okay, and then simplify if possible. And we'll write a little step here. Before we multiply here, our intermediate step is find any domain restrictions. We'll do that as soon as we factor. So looking at our expressions here, let's go ahead and take a look at what we have, starting with example 2, and then we'll move on to 3 and 4 here. Very first thing we want to do is factor. Now, I noticed that up here on the top, I suppose 8 times x cubed times y, this is already written as a product of factors, and as is all of these right here, as are all of these. And so since they're already factored, what I'm going to do is I'm going to go ahead and I'm going to multiply them straight across. So 8 times 7, of course, we get 56. X cubed times x to the fourth is x to the 7th. And we would get y to the first times y to the third, y to the fourth. Whereas on bottom, our 2 times our 4 give us an 8. X times no x's, well, that'd be just an x there. And y squared times y to the first is y cubed. So looking at something like this, we're going to say, well, what common factors do we see? Now, I recognize that 8 and 56 share a common factor of, well, 8. So what this means is our 8 is going to become a 1, and our 56 is going to become a 7. But likewise, when we look at our x's and our y's here, it looks like one of our x's down here cancels out with one of our x's up here, leaving x to the 6th. So I'm going to rewrite this. 7x to the 6th here, and this is all over, well, 1's so far. This would become a 1. And then y to the 4th over y to the 3rd. All 3 of these y's are going to cancel out with 3 of these y's, just leaving y to the 1st here. So we get y to the 1st, and this is all over 1. Or in other words, we could say 7x to the 6th, y. So now looking at this, and looking at our initial expressions, one thing we want to make sure we do is restrict our domain if necessary. And I do notice here that over here we would say that if I set 2xy squared equal to 0, well, then this only is true if we divide both sides by 2 here. The 2 is inconsequential. We still get 0 on the right. We get xy squared equals 0. So either x equals 0 or y squared equals 0, which that's easy to solve. Just take the square root of 0. We get y is 0. So we would say that our domain must exclude an x value of 0 and a y value of 0. And also true over here, we see that we have no variable expression in the denominator. So this won't have any additional restrictions on our simplified form. Okay. So let's take a look at these next two examples. And these are a little bit different because what we saw over here were already factored expressions. Over here, we're seeing some that we're going to have to factor on our own. And so we've got some unique things happening here that I want to make sure that I point out in these examples. Starting with number 3 here, it says find our product. The very first thing we want to do is factor the top and the bottom. So I noticed that at least between these two terms here, we have a common factor of 3 and a common factor of x. So greatest common factor is always a good place to start if you can factor a greatest common factor out. So we get left with 1 minus x. And this would be good to check. We would get 3x minus 3x squared back if we did redistribute this. So now looking at the denominator here, if it factors, which I think it does, a negative 5, two things that multiply out to be a negative 5 that add up to be a positive 4 would be a positive 5 and a negative 1. Something like this here would be our factored expression of this ratio on the left. Now the ratio on the right, the interesting thing is the bottom's already factored into 3 times x. The top is not yet factored, so it looks like 2 factors of a negative 20 that add up to be a 1. Well, that would have to be a 5 and a 4, and it's looking like the 5 is going to have to be the positive 1. Whoops. And 4 is going to have to be negative. So with this being factored, the very first thing we want to do here is assess the situation. We want to say, are there any restrictions here? So if you were to set x plus 5 times x minus 1 equal to 0, then this would only ever equal 0 if x plus 5 equals 0 or if x minus 1 equals 0. So our restrictions here in terms of domain are x cannot be negative 5 and x cannot be a positive 1. But also likewise, we would say that 3x over here can also not equal 0. So we would say that if 3x equals 0, then x equals 0. This is another x value that we must restrict from the domain. So now we've factored it, okay? We've restricted our domain. What I want to do is now just multiply straight across. So on top we get this, we get 3x, okay, times 1 minus x times x plus 5 times x minus 4, okay? And this is all over x plus 5, x minus 1, so x plus 5, x minus 1, times 3 times x. So in terms of common factors, I hope that you've spotted this one that cancels out directly. But also one thing I want to point out here is this. These factors would cancel out if I could get my x minus 1 to switch orders up here. So in order to switch orders here, to switch the order, factor out a negative 1. So that's what we're going to do as our method for getting a difference to switch orders. We're going to factor out a negative 1. So what this looks like instead is, I suppose, if I were to take this and let's move this here. Oh, well, it doesn't want to let me move it. So I'm going to go ahead and leave this where it's at, but I'm just going to go ahead and I suppose write over the top if it'll let me write. Okay, yes. So with what we have here, we have 3x, and if we're going to factor out a negative 1 here on top, essentially we would say times negative 1 times, now this would become an x minus 1 instead of a 1 minus x, and we would have an x minus 4 here. And then on bottom we were left with this x minus 1 times 3x. So with what we have left, our x minus 1s cancel out now, and what we end up being left with is also our 3x's canceling out, I suppose. We get left with a negative 1 times an x minus 4. So one thing that I want to say here, I suppose, is this. If you wanted to switch the order of anything around, like 1 minus x, you could always say that it's really easy to just say this is negative x minus 1, or the opposite of that. So what we get left with is here. This is our simplified expression. And what I want you to notice is that our denominator was 1. It's numerical. It has no variable expressions in it. So it's never going to have any x values that cause it to be undefined. So our restrictions stay as what we had to begin with. Okay, so for this last one, we're going to look at what happens when you take a rational expression divided by just a polynomial. And so this is really kind of easy to handle. What we do is we just go ahead and take it upon ourselves to turn this polynomial into a rational expression. So looking at what we have, let's go ahead and start by factoring the top and the bottom. Now, x plus 2, that's kind of x plus 2. Excuse me. Now, when you look at x cubed minus 27, here's one thing I want to do, because it's probably been a while since you factored a sum or a difference of cubes. But we can factor sums and differences of cubes. It's just that here's our rule. We say if it's a sum of 2 cubes, then we're going to write the numbers that we cubed to get a cubed and b cubed in a binomial with the same sign as what we started with over here. So we have a plus b there. If we were to have a difference of 2 cubes, we would just say the cube root of a cubed minus the cube root of b cubed goes in our binomial here. And what we get is a trinomial on the right. Now, a couple things I'll say about this trinomial. Since it's a trinomial, it has 3 terms, and the last term is always positive. In terms of finding the first sign that we have between the first and second term, it's always going to be the opposite of this sign here. So we're going to get a minus here if this was a sum. We're going to get a positive here if this was a difference here. So filling the rest of these in, here's how it works. You just take this first thing times itself, a squared, and this is true for both of them. Then you take the first thing times the second thing, a times b, so ab, ab. And then we take the second thing times itself in that binomial, we get b squared. So with respect to what we get here in terms of a factor, I would say, well, what I get is this is a difference of cubes. So I get a binomial where the cube root of x cubed is x and the cube root of 27 is 3. Or in other words, these are the things I could cube to get x cubed and 27 respectively. And because this is a minus, we'll put a minus here. And then everything over here, I suppose we get a positive here, and this would be a positive because of this negative here and its opposite relationship. But we would say x times x times 3, 3 times 3. And this would be our factored form. Now on the right side, you'll notice that we have this x squared plus 3x plus 9. And I don't know if you've tried this yet as I was factoring that difference of cubes, but you'll notice that this thing here is just not a factorable trinomial. And so since it's not factorable, we would say that it is prime, since its only factors are 1 in itself. But looking across here, you can see that these two factors cancel out. So in terms of domain, really quickly, let's go ahead and sketch out our domain. If we set x minus 3 equal to 0, we get the fact that x cannot be equal to positive 3. And if we set x squared plus 3x plus 9 equal to 0 here, what I want to point out is when you factor a difference of cubes or sum of cubes, this always ends up being a not factorable thing there. And if we were to actually take a look at the picture of this x squared plus 3x plus 9, let's go ahead and take a look at that x squared plus 3x plus 9. I want you to see that in terms of zeros, x squared plus 3x plus 9. Okay, this right here has no x-intercepts. In other words, it has no x values that cause it ever to be equal to 0. So when you're dealing with something that is a sum or a difference of cubes, the only real 0 you're going to get is from this binomial part right there. This part right here is not ever going to be restricted in terms of real number values. So our simplified form of this, we would say, is x plus 2, okay, was the only thing left on top, over x minus 3. And our restriction here is also x cannot be equal to positive 3, which we've already listed. Cheers.